So, electrical conduction in the heart refers to the electrical signals that go from cell to cell in the heart. This happens in the form of action potentials, which get sent out by the pacemaker cells in the heart. The pacemaker cells, also called conducting cells, are a relatively tiny group, only about 1% of the heart cells, but they're a pretty influential minority. Their special ability is that they're autorhythmic, which means that they're able to continually generate new action potentials that go out to the rest of the heart, which are the other 99%. This is different from how it works in skeletal muscle cells, which get their action potential signals directly from neurons. The cells that receive the cardiac action potential from the pacemaker cells are called myocytes, and they make up the myocardium, which is the muscular middle layer of the heart. Myocytes are also called contractile cells, because they contract and that's how the heart pumps blood. Action potentials are initiated by depolarization, which is the opposite of polarization. In this case, polarization is when there are more positive ions outside the cell than inside. This difference in charge is called the membrane potential, and is negative since there are more positive ions outside the cell. So depolarization is when the membrane potential gets smaller, making a cell slightly more positive than it would normally be. Imagine a negative, gloomy cell experiencing a brief moment of joy. If one cell after another depolarizes, then there's a depolarization wave, which is just like a crowd of people doing the wave at a football stadium. So there are a group of pacemaker cells in the sinoatrial node, or SA node, which is a small sinus or cavity tucked up into the right atrium. During each heartbeat, one pacemaker cell out of the group will automatically depolarize first. In fact, each heartbeat might be led by a different cell in the group, but eventually at least one of them will fire because they're all autorhythmic, meaning that every pacemaker cell has the ability to self-generate a new action potential, given enough time. So as a group, the pacemaker cells of the SA node act like a drill sergeant that gives orders to the rest of the heart. They decide when the heart contracts and when it relaxes, so they set the heart rate. The depolarization wave that comes out of the SA node moves really fast through the pacemaker cells throughout the heart, and moves more slowly through the atrial and ventricular myocytes. Some pacemakers lie along atrial internodal tracts, also called Bachmann's bundle, which connects the SA node to spots in the right and left atria, so that the depolarization wave can quickly reach atrial myocytes in both atria. When the atrial myocytes get depolarized, they contract, which pushes blood from the atria into the ventricles. While this is happening, the depolarization wave also travels from the SA node through the pacemaker cells to the atrioventricular, or AV node. Conduction velocity slows way down at the AV node, and this happens for two reasons. First, the AV nodal cells have very small diameters, which increases resistance to electrical flow. And second, the AV nodal cells use the relatively slower opening calcium ion channels rather than the faster opening sodium ion channels. The AV node is the only point where an electrical signal can go from the atria to the ventricles. And since the depolarization wave causes muscle contraction, this slight conduction delay is crucial in allowing the ventricles to have plenty of time to fill with blood before they contract. So let's say that for some reason the conduction through the AV node is sped up. Well, in that situation, there's less time for ventricular filling, and so there'd be a decrease in stroke volume and cardiac output. From the AV node, the depolarization wave travels through the conducting system of the ventricles. First, it goes to the bundle of His, and then into the left and right bundle branches and into the Purkinje fibers. The Purkinje fibers are the final bit of conductive tissue that spread the depolarization wave to the rest of the heart. The His-Purkinje system conducts the depolarization wave really fast, and this is important because it makes the heart contract in a coordinated way. If the timing was slightly off and the ventricles didn't contract all at once, blood would sort of slosh back and forth, rather than getting forcibly pushed out to the lungs and body. One really cool thing about the heart is that if the pacemaker cells in the SA node fail to fire, there's not only a plan B, but a plan C and plan D as well. Pacemaker cells in the SA node have short action potentials and short refractory periods. So right after depolarizing, they want to depolarize again. That's called the firing rate. And at rest, the SA node has a firing rate of 60 to 100 depolarizations per minute. It turns out, though, that there are pacemaker cells in other parts of the atria that have a slightly slower firing rate of 60 to 80 depolarizations per minute. There are also pacemaker cells in the AV junction that have a firing rate of 40 to 60 depolarizations per minute. And pacemaker cells in the ventricles, specifically in the bundle of His and Purkinje fibers, that have a firing rate of 20 to 40 depolarizations per minute. So if the SA node fires on time, then it resets all of the other pacemaker cells, and that's why it sets the pace. If the SA node doesn't fire, then atrial pacemaker cells finally get a chance to start firing, and they get to set the pace, resetting the pacemaker cells in the AV junction and ventricle. If the atrial pacemaker cells fail, the AV junctional pacemaker cells take over. And finally, if all the other pacemaker cells fail, then the ventricular pacemaker cells start pacing the heart. Once any of these groups of latent pacemaker cells steps up, it's called an ectopic pacemaker, or ectopic focus, meaning that the pace is being set from a place other than the usual spot, which is the SA node. Alright, as a quick recap, pacemaker cells in the SA node send a depolarization wave through the atria so they can contract together, as well as to the AV node where there's typically a delay so that the ventricles can fill with blood. From there, the depolarization wave races down the bundle of His and Purkinje fibers and spreads out through both ventricles, which allows them to contract together. If the SA node fails, other pacemaker cells in the atria, AV junction, and ventricles are ready to step in to take over.